Good morning. Welcome back. How did you enjoy studying for your other classes this weekend? I know that you grade yourself harder in your mind than I typically do, right, when it comes to grading exams. I know you've been talking to each other and psyching each other out over what the possible answers could have been. I've graded the exams as predicted. It's a bit of a bloodbath. So just expect that tomorrow, right? Bring tissue, bring whatever, right? This is hard stuff, right? And so scores, again, predictably are lower than they were on the first exams. On average, some people went up, some people went down, right? But you'll get to find out tomorrow. We'll do the test autopsy. We'll figure out what I did wrong. We'll figure out what you did wrong, what you did right, all that kind of stuff, right? So keep that in mind and hang on until tomorrow. Moving forward, test autopsy tomorrow. We have chapter 7, which I'm going to do my best to cover today because I want to leave room for chapters 8 and 9. Chapters 8 and 9 are pretty big. In order to speed things up just a little bit, okay, we're going to do section 7.8 in next week's lab when we do an entire lab on the center of mass. And then I'm going to strip out anything that has to do with two-dimensional collisions. They're kind of nasty. They're not going to do you very much good. And so this is one of the places that I can sort of pull this content out and you're not going to miss anything. And we can speed things up just a little bit. So what we've been doing really for the entire semester so far is giving you a series of toolboxes. We gave you kinematics, we gave you Newton's laws, and then we gave you energy. Okay? So that's 3 out of 5 toolboxes we are learning this semester. Momentum in chapter 7 is another toolbox. And this one's, dare I say, nice. I mean, you probably don't trust me anymore when I say things like it's going to be nice or it's going to be easier and that kind of stuff. But momentum is nice in the sense that students have told me this is a pretty straightforward idea. Unlike energy, which can be sometimes a little bit nebulous, momentum, you can kind of just nail this one straight from its definition. We use the symbol lowercase p to talk about momentum, because everybody knows that momentum is spelled with a silent p at the beginning, right? No, I have no idea why we use the symbol p. But in order to have momentum, what do you need? You've got to be moving, right? If you're not moving, you don't have momentum. And that was part of the problem with Newton's laws, wasn't it? It wasn't just the motion that was important. We had to actually know how the motion was changing. And what the heck does that mean, Mr. Balogh? It's hard to get our brains to go beyond is it moving to how is that motion changing. Here, with momentum, we can just focus right on the motion. Is it moving? It has momentum. If it moves faster, it has more, right? How do you have zero momentum? You just don't move, right? Okay. We really can't say zero mass. The only thing that has zero mass is light, and we'll get to that in physics 2b. But that's nice, right? Now, one not nice thing about momentum. What's sort of on what's back? Yeah, the vector signs are back, right? So directions are going to make a difference in what we talk about here. Momentum is a conserved quantity. So we're going to leverage some of the skill and problem-solving methods that we did with conservation of energy, meaning that we got to have like an initial and final and all that sort of stuff. But that will come when we start doing some examples. One sort of, I don't know if can call this a segue, tangent that we need to take, is actually a very important tangent, is how this links back to what we've done before. Because when Newton first wrote down his second law, right, all those forces adding up to mass times acceleration, he actually didn't do it that way. That's more of a kind of a modern interpretation. what he first did was he talked about a change in momentum in time. Newton was all about this momentum, about a quantity of motion something has. If it's not moving, it has 0, but if it is moving, and it's like if you've got a train moving at 5 miles an hour versus a car moving at 50 miles an hour, it's possible that the car could have more momentum. It just really depends on how fast something's going and what the mass of the different masses are. So Newton was trying to capture this idea, but one of the things that he discovered is that changes in momentum are all about how long forces are applied in time. So we've got to talk about this interplay between force, time, and changes in momentum, because we have a different name for the change in momentum, and that is impulse. So impulse, try not to lose sight of this, because we're going into that region of, oh my gosh, something's changing again. And it's not just what it is, but how much it changes. Your book uses the symbol capital J, which is very fair, okay, to talk about a change in momentum. And I usually don't use capital J, I usually just use delta P for me. I don't know, just makes more sense. But all of those things are equal to the impulse that something has. And usually, when it comes to talking about momentum exchange, we're talking about objects that are colliding with each other. So, important safety tip here, you got it. When a physicist says something collides, we mean that it's interacting in some way. They don't necessarily have to touch. Can you think of any examples where things collide but don't touch each other? Yeah, right? It's kind of hard, right? Because as soon as I say the word collision, what's the first thing that sort of pops into your head? Car crash, right? Okay, collision center, come get your car fixed, right? That term collision has become synonymous with things crashing together. And I should note here, in all seriousness, we're going to be talking a lot about crashes today. And so for anybody that's been a victim of a car crash or been through that, I feel your pain, right? It's not a pleasant thing to remember. But we are going to be talking about it, so prepare your minds. So a collision is any interaction between objects. So basically any time a force is happening. In physics, we talk about the collision that occurs between planets and suns. Like, we're not literally talking about planets crashing into suns. They orbit, right? And there's an interaction there. And I know it sounds kind of weird, but for us, collision has become this more general term. So I apologize if I say something collides and it never touches each other. I mean that they're interacting with each other. All right. So in a collision, we'll go back to regular normal collisions. In a collision, right, we're going to talk about how momentum is conserved. You can't start with end up with more than you started with, and vice versa. But what a lot of people tend to focus on is the impulse instead, without ever realizing it. And what do I mean by that? Let me just talk about an example here. So let's say I have like a mug of hot cocoa, a coffee mug, something like that right here, right? Nice ceramic mug, okay? And I'm clumsy and I drop my mug of hot cocoa over the tile floor in the kitchen, right? Kitchen floors tend to be hard, right? You don't put carpet in the kitchen. Unless you're crazy, right? So the glass would shatter over the tile floor. But if I had carried my hot cocoa in the living room where there's a rug or a carpet or something like that, right? And I drop it, there's a good chance that the coffee mug or the cocoa mug wouldn't break. Why? Why does it break on the tile floor, but not the carpet?
So the hairs of the carpet kind of absorb that force?
Okay, yeah, we talk about how the carpet is like cushier. It absorbs the impact, right? What's actually happening there? So I take an object, any object, right? And I have a set distance over the floor, right? It has potential energy, gravitational potential energy. If I let go, that potential energy is going to be converted into kinetic energy. We know that no matter what mass the object is, it's going to be going, right, at the same speed. Whether you drop an elephant or a mouse, they're all going to hit the ground same speed if they drop from the same height. So in both cases, if I drop the coffee mug from the same height, it's going to have the same change in momentum before and after the tile floor versus the carpet. So if the mug comes, that's not a very, there we go, that's a coffee mug, right? Okay, falling side down, right, the handle's up, okay? On the tile floor here, right? And then I have the carpet. The coffee mug is gonna have some initial speed, velocity going into the floor, right? And eventually it's going to come to a stop, right? It might come to a stop in many pieces or one part. But the initial speeds here and the final speeds here are exactly the same. The change in momentum, final minus initial, right? 0 minus the initial. Change in momentum over here is final minus it. This is all exactly the same, right? The amount that the momentum changed is the same in both cases. Which one of these experiences the greater force? It's not equal. And here's the trick. How do you know that the one on the tile experienced more force? It broke, right? The force that was applied to the one on the tile was much larger than the one on the carpet. So we know that the force is bigger for tile, and the question now becomes why? What's the only other thing that we can play with? Momentum's the same. Forces are different. What's the third thing in this relationship? It's time. What's the difference between the cup landing on the tile versus landing on the carpet? Aiden said it. What does the carpet do? It compresses, it squishes, it absorbs the impact. All of those words are suggesting that the force is smaller because the time it takes to change the momentum is longer. When that cup hits the tile floor, there's hardly any time in that interaction. The force gets applied all of a sudden. Whereas when the coffee cup strikes the carpet fibers squish down, and it takes a longer time for those carpet fibers to compress. And if the time over there is bigger and the change in momentum is the same, what must the force do? It has to go down. In this relationship of impulse, right? You have your impulse, you have your force, and you have your time. If the force is big, if the time is big, the force is going to be smaller, and vice versa, right? If your time is small, then your force is going to be big, if you keep the change in momentum the same. What are airbags for in cars? What's their purpose? No?
Keep you alive.
Keep you alive, right? So how do they do that? Anybody that's ever been in an accident where the airbag is deployed will testify that it does not feel good to have an airbag go off in your face. It feels like being punched. Because what's actually happened is a small pyrotechnic has blown up in your face. There's a little charge inside of that airbag, okay, inside of the steering wheel and the other parts of the car. And when the car's circuitry detects a collision, in the microseconds it takes for it to go, oh, something's happening, it will fire that pyrotechnic, and that pyrotechnic will provide the expanding gases to get that airbag fully deployed before your head has even started making a motion towards the steering wheel or the side of the car or the windshield or anything else. And so it happens fast, and you end up choking to death on all the talcum powder and baby powder they put in those things to keep airbags got to stay in that steering wheel for what, 10, 15, 20 years sometimes, right? You want to make sure that if there's going to be something that 100% deploys when it's supposed to, and 100% doesn't deploy when it's not supposed to, right? You got to engineer this thing to work. And so you got this cloud of dust, you feel like you've been punched in the face, okay? But the key thing is that airbag is there to do what? Absorb the impact. And now what do we mean by absorb the impact? If you're going at 50 miles an hour and you run into a wall, your change in momentum is just going to be 50 miles an hour times your amount, right? To zero. We can't change the change in momentum. It is what it is. But we can control how long it takes for you to come to a stop. And what happens if we increase the time it takes for you to come to a stop? What happens to the force on you? It goes down. And that's what we're trying to do, right? Force, large force on human body, bad. Right? So this is the importance, right, of understanding what impulse is. Impulse is this relationship between changing momentum, the forces that are being applied to objects, and the time it takes for that force to be applied. We can increase it. Some of you may not have known this or realized this, but all cars built after about 1993 come from the factory pre-broken. Some of you are like, I knew it. I knew that my car was 11. No, what do I mean, pre-broken? There's safety features on the car that will absorb the energy of an impact. No?
Oh, the crumple zone?
The crumple zone. These are parts of the frame. What parts of a car don't matter to passenger safety?
The roof?
Well, actually, the roof matters a lot to passenger safety. It's the thing that keeps the passengers in the car.
The engine and the engine bay?
The engine and the trunk. They are not crucial to passenger safety. They allow the car to go, right? Okay, but in terms of the things that you can compromise in a crash, and you have a choice as an engineer sitting there go, okay, well, we can hurt humans or we can hurt engine. What do you pick? Pick engine, right? So cars by design have these zones built into them that in the event of a crash, those parts of the car will buckle and deform. But the passenger compartment won't, or at least not as much. I learned to drive a car. So my very first car was my family's International Harvester Scout 2. Now, for those of you who have no idea what I'm talking about, International Harvester is a farm equipment company. Okay? They make tractors. They also make big rigs. Some of the big rigs you see on the road still have the International symbol on the front. In the early 70s, they decided to make a Jeep. Everybody was making Jeeps, and so International wanted to get in the car market. They made a Jeep. So what they did is they took one of their tractors, okay, and they put a Jeep frame around it. And that was the car, okay, that I learned to drive on. To be clear, I was not learning to drive in the 70s. The car was from the 70s, right? So it was made in an age when, like, people in Detroit, I'm convinced, like in Detroit, were handed chisels and hammers and a big block of iron and say, carve a car out of that. Because cars from that era were big, they were heavy, and if I hit something with my Scout, it lost. Like, not the Scout, the object I hit would lose. Right? As a matter of fact, it was perfect because my dad never knew if I had wrecked the car because all I had to do was get the hammer out, bang the frame out, and I'm done, right? Like, but the tree and everything else was gone, okay? Nowadays, okay, and when a car hits something, I'm talking about like If a car hits those little concrete things, those annoying concrete things in the parking lot, right, that you pull up and the front part of your bumper scrapes, right, okay? It's like everything falls off the car. You can, back in my day driving those cars around, if there was a head-on collision at 30 miles an hour, there were body bags being taken away from the accident scene. Nowadays, you can see collisions on the freeway at 70 miles, not head-on, but you can see collisions at 70 miles an hour, and you see people after the collision walking around on their cell phones calling their lawyers, right? And there are pieces of car everywhere for half of a mile. More people survive faster crashes today because cars are designed to fall apart in a crash. And in falling apart, what are we buying? Time. We're increasing the time it takes for those cars to come to a stop. And by increasing the time it takes for that car to stop, we are saving lives because we're reducing the force that is exerted on those passengers. So let's do an example. How many have ever noticed these? What are these? Sand or water barrels, okay? And what are they doing in this picture? What are they protecting? The pole. Very good, right? Okay? You'd like to think that they're protecting the humans that try to run into the pole, right? I swear, officer, the telephone pole just dumped in front of my car, right? Okay? So, the skeptic in me is saying they're there to protect the pole, right? But hopefully they're also there to protect the human, right, in the car that might be running into the pole. How are they protecting the pole or the human? Adding more time for the collision to take place, right? Rather than sort of an instantaneous smack up against the pole, we gotta hit a whole bunch of barrels, hopefully taking more time to slow the car down. So what I did is I went and took some data, right? And I rounded some numbers and things like that, okay? But we've got a car moving at about 55 miles an hour, okay, coming and hitting a wall. And we're gonna do a comparison here. We're gonna do two calculations. We're gonna do a calculation where the car just hits the wall, right? Comes to a stop in half of a second. That means from the time the car collides to the point where everything stops moving is half a second, which actually it happens faster than that, but I rounded the numbers just a little bit to make the calculations easier to do. And then we will do the same calculation, the same exact thing, but we will add 1 second, simulating the fact that maybe water barrels are helping to add time to this situation. Okay, so I'm gonna visualize just a little bit. Please forgive my lack of drawing skills, but there's the car, right? And it's going to run into the wall, okay? And the car is going at 25 meters per second, and I'm going to call positive to the right, because why not? And remember, vectors here, although I'm about to strip out all the signs, because they're just asking us, right, find the force. What direction is the force going to be on the car? If I've drawn it this way, what direction is the wall going to push on the car? To the left, right? Okay. So we're not be surprised if we come up with like a negative sign on this, right? It just means it's pointing to the left. Okay. So to do this, to find that force, I am going to use my momentum force time relationship, the impulse relationship. And for both cases, the change in momentum is exactly the same. It's the final minus the initial momentum. Well, how fast is the car going after it hits the wall? 0, right? It comes to it finally. Finally, we can say something hit something, it comes to 0, right? We've been wanting to do it this semester. Minus, and then initial momentum. That'll be the mass of the car times the initial velocity of the car. All right, well, that's negative 1,500 kilograms. And then the velocity of this car is positive 25. Positive meaning that it was moving to the right. Okay. Units. What are the units of momentum? Just a little sidelight here, okay? Well, momentum is mass times velocity. What's the unit of mass? kilograms, what are the units of velocity? Meters per second. So there isn't another name for that. So a Newton is a kilogram meter per second squared, right? But in terms of momentum units, it's just kilogram meters per second. It's kind of a mouthful. It is what it is. Although, I would submit to you or suggest that there's an opportunity here, right? We could come up with our own name for it. Maybe we could call a kilogram meter per second, I don't know, a Balogh, right? So, I mean, I'd be flattered and all that kind of stuff, but what would the plural form be? Would it be Baloghs or Balognians? Maybe, on second thought, maybe we'll just stick with kilograms meters per second. I'll let you decide how many times I was bullied in elementary school by my last name. All right, so kilogram meter, oh, where were we? Oh, yeah, we were calculating this. This is 1,500 times 25. I got 37,500 kilogram meters per second. And the negative sign, what's the negative sign on the front there mean? Yeah, it's pointing to opposite the direction we call positive, right? So at this point, I think I'm going to drop my minus sign. I'm just looking for force, right? Magnitude of force. I know it points to the left. They ask me the direction, I can say left. Okay, so case A, right? And in both of these cases, we are going to solve this for the force, which is going to be the change in momentum over the change in time. All right. So the force, change in momentum over change in time. The change in momentum, 37,000. Boy, I didn't use green. F equals delta P over delta T. All right. 37,500 all over half a second. That gives me 75,000. And what would the units here be? I'm solving for force, and I've put everything in standard units. It should come out in newtons, right? 75,000 newtons. So that's without the barrels. 75,000 newtons. Oh, I didn't write down what that is equivalent is in pounds. I wrote down the difference in pounds. We'll get to that in a second. With the barrels, I take 37,500 and I divide by 1.5 to get 25,000 newtons. So that right there is a 50,000 newton difference, right? We saved 50,000 newtons of force by adding 1 second to the overall time it takes for this car to come to a stop. 50,000 newtons is about 11,000 pounds of force. So if you woke up today and somebody said, look, we're going to give you a choice. You're going to have a car accident today, but you can choose whether to have an extra 11,000 pounds or not. What would you say? Right? 11,000 pounds is bad. What is that, like 3 elephants? Okay. Probably not. It kind of depends on, right, total amount. But 25,000 newtons is big, right? But when it comes to people surviving things, there's a lot of other factors that need to be taken into play. But I posit to you that an excess 11,000 pounds of force is probably going to help or hinder survival, depending on which way it goes. All right. I need two volunteers who are willing to put their bodies and lives on the line for science and will not be harmed in any way. Anybody? Anybody? Aiken, you can come up. We need one other person. Aiken can't do it himself. No? You just want to see Aiken bite it. Juan? Thank you. Come on up. All right. Let's see. Juan, why don't you stand right there? Or Aiken, you stand right there. Juan, I just need you to stand. Okay. So what you guys are going to do you're gonna take this sheet, okay, you're gonna hold that side, walk that way. And you're gonna hold this side, right? Yeah, that'll work, okay, so you're gonna hold that up, but you relax your arms for just now, I need to talk a little bit. What I'm gonna do is I'm gonna take this glass beaker right here, okay? And I'm gonna throw it at the wall. So if I threw it at this board right now, what would happen when it hit? It would shatter, right? Okay. So what we're gonna do instead is I'm gonna have my two lovely assistants here hold this sheet up, okay? So that I throw it into the sheet instead of the wall.
How much tension should we try to go?
Yeah, we'll get there in a second. Still work, okay? Right? But we also have to make sure it's not gonna hit the floor. So the other thing I want you to do is take this other end, okay? And like, you're gonna hold one end up high, and then this end you're gonna hold up just enough so that there's like a little cup. Does that make sense? Right? So I'll throw it right, and ideally it'll land it. Okay, you can put your hands down because I got tough one. Okay, but before we do that, we do need safety protocols. So there's good news and there's bad news. I have enough safety gear, okay? But one of them is a welding mask, right? So one of you is not gonna be able to see what's going on. Yeah, Bond's going for the clear, so take it, you go through up, you're okay with that?
Yeah.
Going in blind?
Yeah.
I'm kidding. Okay, here we go. Here you go. Get those on, you can put the sheet down while you're. I just like to see fear in your eyes. So there we go, got that. Yes, okay. I haven't yet hit a student performing this, so you're in good hands. However, you two need to duck. Okay, but we gotta go. Let's see, yeah, so, okay, so several problems here. I need you guys to step forward, away from the wall, right? I need this to be like, there we go, and I need this to kind of be a cut. Are we good? Yeah, okay, good enough. All right. Drop the front just a little. Keep it back up high. There we go. Are we ready? Okay. I've never played baseball, so here we go. Right? Okay? So, give my hand, everybody. They survived, right? So if I had done that against the board, and I won't because chemistry gets mad when I break all their glassware, that would have shattered, right? Nice and hard. Thank you, gentlemen. So why didn't it break when it went into the cloth? Took more time, right? Took more time. And it's that time that becomes important. Okay, let's talk about when things conserve their momentum, okay? This is the rule. It's a conservation statement, but unlike energy where we took into account like types of energy that weren't gravitational potential energy or kinetic energy, we had that work non-conservative where we could sort of throw everything in. Here we're not gonna worry about any other sources of momentum that aren't accounted for in the problem. So whatever we start with, whatever objects are in our problem to begin with, they stay in the problem. Whatever momentum they have to begin with has to be the momentum that they end with. If we're shooting a cannonball out of a cannon, like off a pirate ship or something like that, before that charge is ignited in the cannon, what is the system? We got a cannon, the thing that's shooting the cannonball, and we have a cannonball. That's two objects that are our system. And together, how much momentum does the system have before the cannon is fired? How fast is the cannonball going before it's fired? 0. How fast is the cannon going before it's fired? 0. Which means that if we start with 0 momentum, what do we have to end with? 0 momentum. What? you fire that cannon, what's the cannonball do? Right? So it's moving to the right really fast. But what does the cannon do? It doesn't stay there. Anybody that's ever fired a gun knows you push the bullet really fast this way, what does the gun do? It recoils. It heads backwards. So if we take the vector sum of a positive momentum forwards and a negative momentum backwards, then it would have to add up to 0. Why does the cannonball go so fast? Why does the bullet go so fast and the gun go so slow? Which one has more mass? The gun, right? So if you fired very heavy bullets out of light guns, what would happen? Bullets stay put, gun go back. Okay? So that's the kind of interplay we're talking about here, right? We have to make sure the vector sum, momentum is a vector, would add up to 0 in that case. And if it wasn't 0 to begin with, we gotta match that number, and we can take advantage of this interplay. Okay? Broadly speaking, there are two kinds of collision out there. There are inelastic collisions, and then there are elastic collisions. The key difference between them is that kinetic energy specifically is conserved in an elastic collision. Now, I know you don't have no appreciation for what that means or what I just said, but think of it this way. An elastic collision is a perfect collision. It's a collision where no energy is lost to anything that we can't keep track of. Whereas inelastic is the more common type of collision. And the way you know is that most problems will tell you. Okay, they'll say things collide inelastically or in a perfect inelastic collision. They'll usually drop some words, but if they're being a little bit more difficult, they will say something along the lines of a car crashes into another car and they stick together, like the bumpers stick together. If you've got objects sticking together, one object being embedded in another, like a bullet being embedded in a block, if there's any kind of deformation, change in shape, pieces breaking off, and that's all inelastic. Just about every single collision is inelastic. In order to have a perfectly elastic collision, you need to have like a perfect set of circumstances where no energy is lost. The closest thing that I can show you, okay, there's two cheats to this I can kind of show you. As long, and the cheat that I'm going to show you right here is as long as my hand is not in contact with the ball, then the gravitational interaction between this ball, the collision that is taking place between the ball and the earth, is elastic. There's nothing being, no air resistance, any of that kind of stuff, right? But as long as my hand isn't involved, that's an elastic collision and interaction. I know that doesn't feel good. You're like, well, you didn't hit anything. Okay. If I drop the ball, that's an inelastic collision. And how do I know? Did you hear it? Where's the energy going? Into sound. Right? Okay? And obviously the kinetic energy was not conserved at all. It had some before it hit, and now it has 0. Right? So, if anybody plays pool, then the striking of pool balls against each other are almost elastic. There's no deformation, but there is one thing that escapes. And what is it? Yeah, it's that clack, right? Okay, that satisfying clack. So what have I got here? I've got, this is actually called Newton's cradle. Otherwise known as the desk toy that ends up on the desk of every CEO or person in a company that thinks they know what they're doing. right? And you've probably seen like smaller versions of this, maybe with magnets in it or something like that. But apparently people that run companies don't have enough to do with their day, so they will sit there, right? Okay, and watches these things. But Newton's cradle was developed as an example of conservation of momentum. Notice, if I take one of these balls and I take it out and I let go, how many balls come out the other side? One. All these balls are the same mass and all that kind of stuff, right? So one ball in equals one ball out. Great, okay? But there's more to it than that. So let me show you how to get a job, okay? You see one of these on an interviewer's desk when you go in for a job, don't even tell them your name. Just sit, just grab it and say, ooh, let me show you how this works. Because what you're going to do is you're going to show them, well, one in equals one out. What about two? What happens if you take two out and you send two in? By conservation of momentum, it has to be two out, doesn't it? Oh. It's hard to hold from the side. We'll do it this way. Right? Two in equals two out. Conservation of momentum. Okay. Now the real test. What happens if I take three? Uh-oh. Ooh, okay. So two a little bit further. One of them a lot. The second one not nearly as much. What does conservation of momentum say? If one in equals one out and two in equals two out, what's three in equal? Three out. Three in equals three out. You must conserve momentum. Okay. What about four? Four in equals four out. What about five? It works, right? You just got a job, right? Show those CEOs and bosses what these things are for, because they're telling us something very, very important about how our universe is put together. The universe wants to conserve energy. It wants to conserve momentum. What you start with is what you end with. And we can take advantage of that in our problem solving. Okay, I'm going to show you a slide and you're going to panic a little bit. Don't panic. Don't panic! One of the things about conservation of momentum problems, this is specific really, this happens in engineering fields and related fields and scientific fields and all that kind of stuff. But in particular for physics classes at the college level, for some reason, the authors of problems want to make the problems harder. Like apparently physics, momentum isn't hard enough. And so they're like, oh, we can make these harder by doing both. This is what they do, okay? I call this the sandwich for momentum problems. So a sandwich ideally consists of a couple pieces of bread on either side, right, top and bottom, and then the filling in the middle. The collision, the thing that's happening in chapter 7, all this stuff that we've been talking about, okay, is in the middle of the sandwich. There are one or two pieces of bread on either side that sometimes have to happen before or after the middle. In other words, a momentum problem in your book, your homework, any of that kind of stuff, has the potential to be not one problem, but three. You might have to do a conservation of energy problem first to be able to do the momentum part from chapter 7, only to have to be followed up by kinematics afterwards. I'm sorry, it just seems to be something, they start pulling all of this together, which actually isn't too bad because this is a warm-up for what's going to happen next chapter. The next two chapters, we're doing everything that you've learned already all over again, but in circles. Real circles, not just the baby circles we've been playing with. So keep this in mind, and I will model this sandwich for you as we go. and do these examples that I have for you, okay? So, conservation of momentum is going to allow us to deal with situations we haven't dealt with before. Like, up to this point, we've always dropped the ball and always said, well, right before it hits the ground, right? We're going to do some analysis. Well, now we can talk about what happens when it hits the ground. That's a collision. I can conserve momentum. I can do a bunch of stuff there, right? So, in this example, we've got a car rolling down a hill, and it hits another car. Conservation of momentum is going to apply only in that moment when the two cars, the car and the truck, are hitting each other. Is there, yeah, okay, delivery truck, right? So I want to visualize, I want to strategize, I want to do it, I want to check it. So visualization, what do hills look like in physics? Yeah, they look like triangles, don't they? So here's my hill, right? Here's my car. I'm feeling very artistic today. It says 13.1 meters high. What does that mean? Vertical, along the slope, what? It's the vertical height. 13.1 meters, right? Right there. Okay, we know the mass of the car is 1,500 kilograms. Collides with the delivery truck. Delivery truck. Okay, goes boom, and we know that this one is 5,000 kilograms, right? So, oh, and then like, sometimes you have to do like a before and after, right? Before, during, after, right? You can do that if you want. I'm not going to do that here, but we got to figure out what's going on. So as part of my visualization, you see I've drawn a picture. Okay, and again, you can draw more. I'll go ahead and draw more than one. Why not? So this is before. Okay, during. Nope. There we go. Boom, boom, boom. Right. Okay. During, and then. After, it's got the car going backwards at 5 meters per second, and then the truck doing something, right? Going some speed forward. Okay. So, and this is after. So I'm kind of like taking frames from a movie, right, or a video. Okay. Before, during, and after. So. What I do, whenever there's a collision, whenever there's an interaction, whenever two objects or more are doing something, I like to start in the middle of the sandwich. I like to set up the conservation of momentum part first, and then try to figure out what my pieces of bread look like. Because it can get a little bit overwhelming, like what do I do, how do I start? Start in the middle. Start with the during. Because the during is going to be your conservation of momentum. Whatever momentum there is initially has to be the momentum you have afterwards. And now we have two objects that are interacting. We have the car and we have the delivery truck. So I'm going to call the car mass number 1, M1, okay, M1. We'll call the truck M2, okay. So I've got M1, V1 initial. And I'm going to put a vector sign on the velocity because that's important. And then I've got M2, V2 initial. That's the total momentum I have before I start. Two objects, they could both have momentum or they could have zero. And then afterwards, I have M1, V1 final plus M2, V2 final. That's the total possibility. Now, are any of these things zero? And how do we know? Does the car have momentum when it strikes the delivery truck? Is it moving? Yes, right? It's going to roll down that hill, it's going to pick up speed, and it's going to hit the delivery truck. Does the delivery truck have momentum? What's the speed of the delivery truck initially? It's 0, it's at rest, isn't it? So that means that I can go ahead and I can say, well, this is 0. Right? I don't have that term. Now, afterwards, are they both moving away from each other? Yeah, they are, right? They've collided, the delivery truck's probably going to get pushed forward, and the car is, we were told the car rebounds and goes backwards. So I can't zero any of those things out, right? But I'm left with M1 V1 initial equals M1 V1 final, which is a known thing now. Do I know the mass of the car? Yeah. Do I know how fast the car is going after the collision, the final? Yeah, I do. Okay. Plus M2 V2, where V2 final is the thing that I want, right? I'm after, this is what I want, and I know M2, I know V1 final, I know M1, I know M1. I've got two unknowns here. I don't know how fast the car is going when it strikes the truck. And I don't know how fast the delivery truck is going after the collision. So if I've only got one equation and two unknowns, I've got to go figure out another one of these unknown things. And it's the V1 initial, the speed that the car is going to hit the truck, that I'm going to have to go reach into another toolbox to figure out. So my sandwich meat, the thing here in red, the thing in the middle, is informing my strategy. I've been strategizing with this conservation of momentum. And I say, okay, well, I don't know what this is. This is what I want. I'm solving for this. This I don't know. I've got to go figure out what it is. How am I going to figure out what it is? I'm going to look at my before problem. I'm going to ask myself, is there a way I can figure out how fast this car is going when it rolls down the hill? Have we done this problem before? Yes. Kinematics, Newton's laws, energy. Pick a toolbox. All you've been given is height. You don't know time, you don't know acceleration, and you don't want to draw a free body diagram. So what do? Kinematics? No, we don't know the acceleration. What should you read for first? Energy. If energy can get it for you, you can usually get it faster than anything else. So if I reach for an energy, so now I'm not doing chapter 7 anymore. Now I'm back in chapter 6. You thought it couldn't come back to hurt you, but here it is. So now I'm going to do a problem where I set like an initial point, a final point, and a 0. And I have my work on conservative equals energy final minus energy initial. There's no friction. My final is kinetic energy when it gets to the bottom. My initial is potential energy that it starts with at the top. Mass of the car doesn't matter. And when I do some algebra, this is equal to the square root of 2gh, which is a result that we've gotten actually several times, because it's the answer for anything that gravity is pulling on. How fast is it going to be going when it falls to a vertical height h? The answer is square root of 2gh. So I can go find out what that is. Maybe. Thought I had this problem in my notes. Sometimes my note pages go places. It's kind of funny. Right here. I just can't read. There it is, 16 meters per second. So now I know how fast the car is going at the bottom of the hill. Where do I stick that 16 meters per second? It's the V1 initial. So now I can come over here and start putting in numbers. This is going to be 1500. And then V1 initial vector sign. Which way are we going to call positive? Now let's call positive to the right. So it comes down the hill, moving to the right, and has 16 meters per second when it gets to the bottom of the hill. So I'm going to put in plus 16. This is 1500. Okay, now V1 final. Which way is the car going after the collision? To the left. So what are we going to put on the 5? A negative sign. Be careful with these signs. They'll get you. They'll get you. Negative 5 plus 5,000 times my unknown V2 final, which is what I want. I can take the vector sign off of it now. I'm solving for it. So, do some calculator, rearrange some stuff, and we get a V2 final of positive 6.3 meters per second. So in the check it step, we sit here, we ask ourselves, okay, first of all, what direction is the truck going? Right or left? To the right. We got a positive answer, didn't we? Do you think the truck would go to the right if it was rear-ended by a car rolling down a hill? Yeah, that's probably what would happen, right? It's not like the car would rebound off and the delivery truck would start moving backwards, right? We'd expect some of the momentum to get imparted to the truck, okay? The fact that the car rebounds delivers even more momentum to the truck, okay? And we've got what seems like, I didn't get a number that was bigger than 16, which makes me kind of happy, right? And if we did do a calculation, right, for the kinetic energy before and after, we would see that they're not the same, right? There was probably deformation and sound and all of that stuff that happened. So when you're doing a conservation of momentum problem, my advice to you is start in the middle of the sandwich. Identify your system, write down conservation of momentum. You're probably going to have like 2 or 3 unknown things in that thing that you write down. But those 2 or 3 unknowns are like a map telling you what to do to get the pieces of bread. Okay? And then when you reach for the pieces of bread, you're doing chapters 1 through 6. Okay? And probably most often chapter 6. How do you know if it's kinematics? Like, what's a dead giveaway that you're going to have to do kinematics?
Horizontal. Acceleration.
Time. Time is 95% guaranteed you're doing kinematics. The only time, the only time time shows up in forces is when we're talking about impulse. Right? Force, time, change in momentum. The only time time shows up in energy is if we're talking about power, watts, horsepower, that sort of thing, right? But if the time it takes for something to happen, or you're given it, if it takes 2 seconds for the car to roll down the hill, boy, that's kinematics, right? So, and then my advice is avoid Newton's second law at all costs if you can. Sometimes you can't, sometimes you just have to do it. That energy first, then kinematics, and then finally Newton's laws in that order. Okay, in the last 15 minutes, I want to do something very different than your book does. I want to be very clear. I am not saying your book is wrong. Your book is correct for a certain level of correct. I want to show you a better way of dealing with elastic collisions. In the book's method, they end up with no fewer than 8 different equations, I think, for dealing with elastic collisions. And in my mind, that is 7 too many. Okay? So what I want to do is I want to give you a result that I don't have time to show you where it comes from. You probably don't care where it comes from. It's actually pretty nifty. It's kind of, you do some magical math stuff, and everything just sort of works out beautifully. But I'll save you from all of that physics and mathematics. I want to show you the safe way to get through elastic collisions. Again, elastic collisions are those perfect collisions. And typically, and I'll do an example of one here in a second, typically there's like 2 unknowns in the problem that you get stuck on. And the problem with the book's method is that those 8 equations only apply to 8 different situations, depending on what's going on. And it can be very hard to determine which equation to use for which situation. I'm going to give you one equation for all of them. This method, this equation I'm about to show you, works for every elastic problem. In elastic collisions, we conserve 2 things. We conserve momentum, and we conserve kinetic energy. Energy is not a vector, so I don't put vector symbols over the top, okay? We can't get away from the conservation of momentum. You're always going to be conserving momentum. So you will have an equation that will be the middle of the sandwich, okay? But if you're told it's an elastic collision, we also have this conservation of kinetic energy. In other words, whatever initial kinetic energy we have has to be the final kinetic energy that we have. If you write all that out for all the things in the problem, it's going to be a disaster because it just goes wrong really fast. There's squares all over the place, and sometimes they're unknown thing. It goes wrong. So what you're not going to do is write down conservation of kinetic energy. Instead, you're going to use this. V1 initial minus V2 initial is equal to V2 final minus V1 final. That equation right there in the box becomes your key to solving every elastic collision problem. Any situation that you are given, whether something's moving or not, this works. You're going to make sure, so you're going to have your conservation of momentum equation. You're going to have the 2 things in the boxes, okay? And you're going to have to do some math to get them to talk to each other. But you got to make sure that you, what I call mind your signs. Notice I didn't write vector symbols over the tops of these things. If something is moving to the right and you call the right positive, make sure you put a positive sign on it. Okay? If it's moving to the left, what sign are we going to put on it? We're going to put a negative sign on it. Okay? So mind your signs. Make sure, right? If something's not moving, what are you going to put in for the velocity? 0. And now you can solve every elastic problem without having to reference 6 to 8 different equations. Some books are even worse where they give you just 2 and then there's a bunch of plus and minuses on everything. It's horrible. I don't know why they do teach it the way they do. They probably have some good reason that I don't realize, but I've been doing this for 2 decades and I've never gone wrong with it. So let's do an elastic collision example. I want to model using this sort of magical mathematical method for you to be able to handle any elastic collision, okay? We know it's elastic because it says it's elastic. If you're not told that it's an elastic problem, it's inelastic. The book's really good about this. I would never try to trick you, okay? I will tell you on an exam if it's elastic or not. If I don't say it's elastic, what do you assume? It's inelastic, okay? But usually we say it's inelastic, all that kind of stuff. Okay. Assume a perfectly elastic collision. Good. Find the velocity of each ball. So there's 2 unknowns, right? We want to find the speed of both bowling balls after the collision. Where do I start? How do I start any problem in physics? Visualize. Get something on the page so your brain can start working on it. Okay? So what I've got is like I've got a bowling ball. Whoops. I've got a bowling ball. The 8 kilogram ball, right? And let's see, it says that this one is moving at 5 meters per second that way. And then I've got my 10 kilogram ball, which for some reason I made smaller, 2 meters per second. What am I going to do with, if I said that the 5 was positive to the right, what am I going to do with the 2 moving to the left? Negative sign on it. Okay, so this is like before, right? During, they've hit each other, right? And then I've got my after, and now I'm sort of guessing a little bit, right? I'm not quite sure. I'm assuming they'll bounce off of each other. They don't have to, but I'm assuming they'll bounce off of each other. Let's see what happens, okay? Before, during, after. Start in the middle of the sandwich. Start with your conservation and momentum statement. Whatever I had before, I have to have after. What do I have before? Well, I've got an M1 V1 initial plus M2 V2 initial. Afterwards, M1 V1 final plus M2 V2 final. So, are any of these things 0? Does the 8 kilogram ball have speed before the collision? Yes. Does the 10 kilogram ball have speed before the collision? Yes. Afterwards, do they have speeds after the collision? Yeah, well, I don't know what they are, but I'm assuming that it's not 0. Right? One of them doesn't. They didn't say one of them stopped. Okay? So there's nothing I can cancel in that equation right there, which means I'm going to put that equation on hold right now because it's big and it's scary and I don't want to think about it. Okay? So what about before and after? Mr. Balogh, you just showed us how we got to reach for like chapters 1 to 6 or something like that to figure out what's going on before and after. Well, there's really nothing going on. Like, there's stuff happening, but it's not like there's a conservation of energy problem I can solve over here. There's no Newton's law problem I can solve over here. But I do know that this is an elastic collision. So I know that I'm going to pull out the mystery equation that Mr. Balogh gave us, which is V1 initial minus V2 initial equals V2 final minus V1 final. Somehow, this equation will save you. And this is how it's going to save you. At this point, put in numbers. Don't try to solve these. I never tried to solve these symbolically. It's not worth it. Okay? You put in numbers at this point. Maths 1, 8. V1 initial. What do I put in for the number? Positive 5. Plus 10. What do I put in for the number for V2 initial? Negative 2. Those are very important, those signs. Equals 8 times V1 final. I'm just going to leave it as V1. And don't like writing a bunch of subscripts. Plus 10 V2. V1 and V2 are the things I'm looking for, right? Okay. Can I clean this up a little bit? What's 8 times 5? 40? And negative 20? So this is a positive 20, isn't it? 8 V1 plus 10 V2. Everything there looks like I can divide it by 2, right? Just to get this as simple as I can. So this is 10 equals 4 V1 plus 5 V2. It looks very sloppy. V1. There we go. So I just kind of made that as simple. You don't have to do all that. I can hear my 7th grade math teacher yelling at me. Simplify, simplify. Over here, in the after. Do I know V1 initial? Yeah, what is it? Minus, so it's V1 initial minus V2 initial. But what's V2 initial? Negative 2. Mind your signs, right? Equals V2 minus V1. I'm just taking the finals off because I'm tired of writing. So what's a 5 minus a minus 2? 7. How important are these signs? Extremely. Keep track of all those minus signs that are floating around. Okay, I now have 2 equations with 2 unknowns. We got the 10 equals 4V1 plus 5V2, and I got 7 equals V2 minus V1. 2 equations, 2 unknowns. This is solvable. We've done worse in this class before mathematically. I'm going to solve, I don't know, I'm going to solve the 7 equals V2 minus V2. I'm going to solve that for V2. And just shove that into my, there's lots of different ways to do this. That's the way I'm going to do it. So what is this? This is add V1. Okay, now I'm doing math, so we'll use a different color. Plus V1 over here, plus V1. So this is 7 plus V1 equals V2, which means that's going to go in right there. And I'm going to continue this calculation up here because I know I'm going to run out of room. 4V1 plus 5 times the quantity 7 plus V1, which is going to be this. 35? 5 right? I don't know. When I started taking calculus, my brain got rid of arithmetic. It's like there was a certain amount of space in my brain, and my daughter in second grade, Daddy, I can do math better than you. And she rattled off all of her times tables, right? Because I can't multiply to save my life. And I'm like, yeah, okay, that's pretty good, sweetheart, but here's some differential equations. She went and complained to her mother. All right, plus 5v1. Okay. What do I do with the 35? Now I'm going to move it over. I want to get everything with v1 on one side and everything that's not v1 on the other side, right? So that's going to be minus 25, right? Negative 35 goes over, add 10. Okay, and then what's 4 plus 5, v1? 9v1. So v1 is going to be minus 25 ninths, or 2.78 meters per second. Check it. What am I going to check? How do I interrogate this answer? What do I do? What's the first question I should ask? The sign. What? Negative. What does negative mean? That means left, doesn't it? Do we expect the lighter ball to bounce off the heavier ball? Seems pretty good to me, right? So, yeah, I'd buy that. 2.78, why not? All right, now that I've got that, I now put that in here, don't I? I know what V1 is, so you know what? Why put it into that hard one? I can put it in over here, can't I? 7 plus a negative 2.78 equals V2. And I do that in my calculator, and I got 4.22. Positive. What does that mean the 10 kilogram ball does? It bounces off and goes in the opposite direction, to the right. Again, sorry, if I slam two bowling balls together, I expect them to kind of bounce off of each other, right? Seems pretty good to me. To recap, when you have an elastic collision, do those two things. Identify the directions things are going, and more often than not, you're being asked to solve for velocity. Sometimes you're asked for mass, like they'll tell you the velocities, but then what are the masses of the things, right? That's just a different math problem to solve, right? But the setup becomes the same. So, that was all of chapter 7. Tomorrow, what's happening? Test autopsy, right? Test autopsies, at the longest, last an hour, which means that you've got a couple hours of freedom after that. You know your lives better than I do, so you do whatever you want with it, but you're welcome to stay tomorrow and get a head start on this homework, right? I've covered everything I'm going to cover in class. We could knock off maybe easily half of your homework in 2 hours, right, if you want to stay for grasp. I'll have computers for you and all that kind of stuff. So just so you know, so you can plan your day, you are welcome to stay after the test autopsy and get ahead. I will see you tomorrow.